Okay, good morning, thank you. So this morning I'm going to finish off. We've had some nice talks on silicon nanowire sensors already this morning, but I'm going to talk about integration of these sensor devices into a package and how we fabricate these things on a more volume scale. So that's going to be important when we take these things to the market and commercialize them and reduce the cost. So just point out where Swansea is for those who don't know. Swansea is there's London. Swansea is about 3 hours west by train from London. And we sit there very nicely on the beach for those of you who would like to visit. Okay, so what we're doing then is we're taking silicon technology, silicon processing technology, and we're applying that to biosensors. So of course we need to do that in a clean room, and the production techniques are based predominantly on photolithography or electron beam lithography, or what I'm going to talk about a little bit more this morning, nanolithography, nano-imprint lithography techniques. Okay. So photolithography, and one nano-imprint technique in particular called SCIL, which is Substrate Conformal Imprint Lithography. It's a new type of imprint lithography process developed jointly by SUSE Microtech and Philips, and enables you to produce these arrays of nanostructures down to about 30 nanometers, but crucially over large areas. So we can produce structures on up to 8-inch wafers. Okay. And what you can see here is an interesting example where you have a particle under your imprint, but the imprint pattern is transferred over the particle. So the nice thing about this process is you don't get voiding as you do in some imprint techniques. Okay, so what we're trying to do then is use these nanofabrication techniques to create sensors. Very simple sensor structure, a channel between two metal electrodes, and then we're going to functionalize this channel. So there's our channel. This can either be silicon or it can be graphene, and we're going to functionalize using a linking molecule. There are several linking chemistries that we use. We use silicon, but we also use a diazonium molecule. The crucial part is attaching this amino group to the surface. There's our antibody detecting our biomarker, and it's a very simple current voltage measurement, changing the conductivity of this channel. Okay, so why do this? Well, it's all about early detection, more rapid detection, okay, higher sensitivity, and by doing that at the point of care, we can provide more effective treatments to patients. Okay, so this is the sensor we've done a lot of work on. It's a sensor for a molecule called 8-OHDG, which is an oxidative stress marker linked to several cancers, also linked to prostate cancer and urine. So what you're trying to do then is fabricate your sensor, have a little cartridge. There's several different types of approach. That cartridge then slots into this reader. You expose your chip to your sample and you get a very simple measurement, and it tells you is your biomarker present or not, and hopefully also at what concentration. So this is an overview of the nano imprint process. We create a master stamp in silicon. So this has your silicon nanowire structures. We then replicate that in what they call a soft stamp, which is using PDMS. We load the PDMS replicated stamp in the stamp holder, and then we imprint it into a polymer resist. And this imprint process, you can see, is done sequentially, so it goes down a little bit at a time, and also the retraction is done sequentially. And again, that avoids voiding or trapping of bubbles in your resist layer. And then you end up with your patterned nanowires on your silicon or SOI, silicon-on-insulator wafer. This is just fabrication of the stamp master, and the crucial point here is that the replicated nanowire is the same as the nanowire on the initial master. Okay, and what indeed you get very, very good replication. So the quality of the nanowire depends really on the initial master stamp quality. Okay, so you can see very nice, neat nanowires, arrays of them, and these are produced over a 4-inch wafer. So this would take you many, many hours to write a pattern like that using an electron beam tool. Okay, this replication process takes only about 10 minutes. Okay, we also fabricate graphene devices. And these are some examples here. Again, the device structure is very similar. We're just simply replacing the silicon nanowire channel with a graphene one. Again, variety of different chemistries. This one we saw similar chemistry in the first talk, but we also use diazonium-based chemistry as well. This is a graphene channel, and what you can see here is the channel before functionalization, which is in the yellow, and then after functionalization, what you're seeing here is the Raman spectrum, and this is the D peak of the Raman spectrum, which indicates increased defect states after functionalization of that graphene channel. This is the graphene functionalization process, and again, using a diazonium molecule to create an amino group on the surface, and we can then electrochemically functionalize that channel. So here are the channels, the functionalized channels. We've made these larger so we can use fluorescence microscopy to image labeled antibodies, and you can see the channels lit up quite nicely in red. We see changes in the AFM topography of the surface, and obviously we see changes in the cyclic voltammetry plots. So this is the final result then. What we're doing here is monitoring the change in the conductivity of the channel at each stage of the functionalization process. So that goes from the initial silicon nanowire to the functionalization processes, and then the important part is the attachment of the antibody, this one, and then finally binding of the target, which is the green one. You see you get quite a significant change in the resistance of the channel on that binding event. And here we have, this is a silicon nanowire based sensor, and we're detecting nanograms per milliliter. You see a fairly linear range in this concentration region. So that was for the 8OHDG oxidative stress marker. We've also done quite a lot of work on HCG, and this is the pregnancy hormone. And using a different sensor platform, different functionalization chemistries, we're able to detect nanograms per milliliter using a current voltage type measurement, and then down to picograms per milliliter using an impedance-based measurement. So once you fabricate your devices, whole wafer devices, dice it up, each chip, this is a single chip, fit it into a little package. This is our first prototype, early prototype. Now we've got more advanced prototype packages, which look a little bit more like the glucose strip sensor that you get for blood glucose testing. We also need to integrate microfluidics to channel any sample, any saliva sample, for example, onto the sensor surface. That's what we're seeing here. We're seeing a little microfluidic pump, this time based in silicon microfluidics. So we've got two electrodes here and here, and we're basically using a voltage to transport solutions, ionic solutions, through these micro channels. We've also done a lot of work on microneedles, and the idea here is that you can stick these microneedles into your skin, and they will extract some sort of fluid, either interstitial fluid or if they're long enough, blood, and then the fluid will channel along some microchannels onto a sensor chip, which will then detect the analytes in that fluid. So that's the idea. Of course, not a new idea. We've borrowed this from nature. This is the mosquito's proboscis, which is sharp enough and short enough to penetrate into the skin without us noticing. Okay. So that's what we're doing, trying to make these microneedles. There, in comparison, is a hypodermic needle, so you can see which one you probably rather have injected into you. So different microneedles are polymer. These ones are polymer. These ones are silicon. What you see, these needles are not actually sharp yet. So the tip is not sharp enough. That won't actually penetrate into the skin very effectively unless you push really hard. So the new design is a beveled needle or sharp needle tip. This is just an illustration, but our initial results are very good. So we've produced this sharp tip, and this actually penetrates very well into the skin, and you can get it right into the skin. These microneedles up to 1 millimeter in length, and we think they're around the longest produced that is in the plane of the wafer. So not cutting into the wafer horizontally, but etching the wafer vertically. Okay. So again, full wafer process. There's a single chip, 10 by 10 millimeters. Still needs some optimization. So the spacing between the needles is very important. Otherwise, they act like a bed of nails and won't penetrate properly. And also the injection site. So where you inject on the body, so where your skin is thinner, obviously you need less pressure to penetrate the skin. So at the moment, we're optimizing different needles for bespoke applications in drug delivery, in sampling, and vaccine delivery. Simple applicator system, we stick that on the end of a syringe, and then we're able to either extract fluid or inject fluid through the skin. So, finish there, and I'd like to thank my group for all their hard work, and thank you for your attention.